Welcome to another Minute Math video. Today's topic, factors and multiples. What is a multiple? Go ahead and take a minute to think about what that definition is to you. What you think of as a multiple probably is not this definition here. The product of a whole number and any other whole number. So what does that mean? So back in probably elementary or middle school, you were taught to do skip counting. A common one that you probably use in your everyday life is skip counting by twos. 2, 4, 6, 8, 10. Another common one, fives. 5, 10, 15, 20. You might skip count by tens. But what these all have in common is that when you skip count, really what you're doing is looking at their multiples. Specifically looking at 2. 2 times 1 gives me 2. 2 times 2 gives me 4. Times 3 gives me 6. Times 4 gives me 8. Times 5 would give me 10. If I skip counting by fives, 5 times 1 is 5. Times 2 is 10. Times 3 is 15. Times 4 is 20. Tens, same pattern. Times 1, times 2, times 3, times 4, and so on and so forth. This is different than a factor. Go ahead and write down or think in your mind or say out loud what you think a factor is. A factor is a number that can be multiplied in a multiplication problem. I tend to think of factors not necessarily as individual numbers in the multiplication problem, but as the pair. So what are the factors of a number? For example, 24. Instead of thinking just one number that I can divide 24 by, I think of what two numbers give me 24. Well, I know if I take 24 and I divide it by 1, I still get 24. I know that 2 times 12 gives me 24. That 3 times 8 gives me 24. 4 times 6 gives me 24. And so these are the pairs. So 4 times 6 is a pair. 3 times 8 is a pair. 2 times 12 is a pair. I just tend to think that this is going to be easier in the long run rather than thinking of individual factors, looking at all the possible outcomes there. Because in most cases in math, it's going to be helpful to have both. But we do have some similar terms to factors and multiples. So some similar vocabulary that you should know include prime numbers. Prime numbers are special whole numbers whose only factors are 1 in itself. In my daughter's math, ABCs of Math book, it has prime numbers, and it defines 1 as a prime number. But that doesn't really count, okay? So the first prime number that we're going to have is 2. We can't divide 2 by anything but 2 or 1. Then it's 3, 5, 7, 11, 13, 17, and we can keep going on and on and on. These are useful for situations where we're asked to do a prime factorization. A prime factorization is the process of finding all the prime numbers that multiply together to equal a composite number. Composite numbers just mean that they aren't prime numbers. Numbers like 4, 8, 24, those are examples of composites. So let's think of our example of 24 from earlier. I want to know what all the factors are that are prime numbers. So if I divide it by 2, I have 2 and 12. But I can divide 12 and get 3 and 4. And I can break up 4 into 2 and 2. Now I can't divide any of these remaining ones any further. So by remaining numbers, I'm specifically talking about this 2, this 3, and these 2's here. Those are all prime numbers. My prime factorization of 24 would be 2 times 2 times 2 times 3. This won't happen very often, but you will see questions like this on the HiSET and the CASAs, depending on which form and variation you get. The next one is least common multiple. It is very similar to what a multiple is. This time, we are looking at 2 or more values or events, if we're looking at a word problem, and trying to figure out when they overlap again. So an example could be Amazon makes deliveries every 5 days, and UPS is going to deliver every 3 days. If they were to drop off deliveries today for me, when is the next time I can expect both of them to come to the house or to the school or to the office? One way that I can do this is I can list out all their multiples. 5, 10, 15, 20, 25, and I could keep going, but I'm going to stop there. And if I need to, I will add more later. 3, 6, 9, 12, 15, 18, and I'm going to stop there. Once again, if we need to, we can keep going. Then the next part of this is, which of their multiples do they have in common? 5 and 3 aren't the same, 6 and 10 aren't the same, 9 and 15 isn't, but 15 does appear in both lists, so 15 would be my least common multiple. Now, that's not the only time least common multiple is going to be important to us. Anytime that we want to take two fractions, we'll say 3/4, and we want to give it the same denominator as, let's say, 5/10. What I'm going to do here in this situation is I'm going to find the least common multiple of 4 and 10. So if you have two fractions, you want to give them common denominators, it is going to be through this process. 4, 8, 12, 16, 20, 24, 28. And then if I need to add more, we can. 10, 20, 30, 40. Now, initially, you probably thought that the least common multiple would be 40. That is a typical gut reaction. Except we want the smallest least common multiple. Yes, 40 would be a common multiple because 4 times 10 is 40. I know that looks like 90. That's 4 times 10 is 40. Just trust me on that one. But we have a smaller number, which is 20. So the least common multiple between 4 and 10 would be 20. We'll look at more examples of fractions later, especially when we get into our next learning objective, which is going to be on adding, subtracting, multiplying, and dividing with any real number. Then the next vocabulary we have is the greatest common factor. The greatest common factor is typically used when we need to evenly split 2 or more different types of items into groups. If we are looking at fractions like our last example, we would be reducing. So what is the greatest factor between the numerator and denominator? And that might be hard to imagine. So let's pick one, like 8 20ths. We would have to figure out what the factors of 8 and 20 are. We have 1 and 8, 2 and 4, and then we're done. And 20, 1 and 20, 2 and 10, 4 and 5. So we want to know what the biggest common factor is. They both have 1 and they both have 2, but they have one more that's even larger, and that would be 4. So we're going to divide both 8 and 20 by 4. This is why factor pairs are important, because now these are the 2 factors left over, 2/5. That would be my reduced fraction using the method of finding the greatest common factor. But fractions aren't the only time where we are going to use greatest common factor. We could also use this in word problems. If you have 125 roses, 75 carnations, and 100 calla lilies, sorry about that, how many bouquets can we make? Well, in order to do this, we need to list out all the factors of each and find the largest one. Some of you might already know what the greatest common factor is, but let's just use this as practice. The factors of 125 are 1 and 125, 5 and 25, 75 is 1 and 75. Now you're probably wondering why I always do 1 and then the number we start with. And that's in case I have a prime and a composite number where they don't have any other common factors. It's always good to be in that habit of writing that one right away, because there might be a time where 1 is your common factor. We also have 3 and 25, and 5 and 15, and 100, 1 and 100, 2 and 50, 4 and 20, 4 and 25, 5 and 20. So if I look through each list, the largest number, or the one that they all have in common, is 1 and 5, but they also have 25. So the greatest common factor between 125, 75, and 100 is 25. that means the most possible bouquets in this example would be 25. You'd have 5 roses, 3 carnations, and 4 calla lilies in each bouquet.